For several lectures now, I've talked about the characteristics and the behavior of atoms. The atomic structure, that's one of the most fundamental discoveries of science. But there's one more topic about atoms that's of vital interest to all of us, and that topic is nuclear reactions. This lecture, Lecture 28, focuses on one of the transforming discoveries of the 20th century. That's the realization that nuclear reactions produce heat and radiation through the conversion of mass into energy. In this lecture, we'll see that the atomic nuclei can be split apart in nuclear fission reactions and combined in nuclear fusion reactions. In a sense, these reactions at the nuclear level are sort of like chemical reactions. You recall that chemical reactions have groups of atoms that can be combined or they can be split apart. And I'll begin, much as we did in the discussion of chemical reactions, by thinking about energy. See, energy drives nuclear reactions. Then I'm going to focus on the two great classes of nuclear reactions: fission reactions, by which atomic nuclei are split apart, and fusion reactions, by which two nuclei are combined into one. And I'm going to close with some comments on the benefits and the risks associated with our growing command over the atomic nucleus. Well, let's start by reviewing the nature of the atomic nucleus. In the last lecture, we saw that an isotope is defined by the number of neutrons as well as the number of protons. And while there are only about 100 different chemical elements, there are about 2,000 different isotopes, as illustrated on this table of the isotopes. Now, this table illustrates every known isotope. On the vertical scale is the number of protons. So each horizontal line is a different element. And then the horizontal scale indicates the number of neutrons. Every square on the chart is a different isotope with different nuclear properties. We've seen in the last lecture that isotopes can experience several different fates, and I reviewed two of these. Almost all the atoms around us are stable isotopes. Those are isotopes that remain unchanged for billions and billions of years. The exact same atoms recycle over and over again, but they aren't ever destroyed. And then there's a second fate for atoms on the Earth. About 1 out of every million atoms in our environment is radioactive. These atoms, these radioactive atoms, spontaneously emit potentially dangerous rays of energy. I told you about 3 different kinds of radioactivity. First came alpha radiation. That's the one in which an atom spontaneously emits an energetic alpha particle with 2 protons and 2 neutrons. That's like a tiny atomic bullet. As a consequence, the element changes. Uranium becomes thorium and so forth in alpha radiation. And then beta radiation is next. In beta radiation, 1 neutron in an atom's nucleus spontaneously becomes a proton, and that remains in the nucleus, and then an energetic electron flies out of the atom. The electron can damage other molecules, including those in your cells, and once again the element changes. And finally, there's gamma radiation. In this case, the atom doesn't change, but it sends out an energetic gamma ray. That's a photon of high-energy electromagnetic radiation. And once again, if your skin absorbs that radiation, it can do cellular damage. Isotopes can experience other fates, though, besides living out their lives in stability or spontaneously emitting radiation. Under special circumstances, isotopes can fuse together or they can split apart, as they constantly do in stars. And on Earth, as we'll soon see, scientists and engineers have learned to help these processes along. Now, think about the fact that some isotopes are stable and some are radioactive. That means that different isotopes have different nuclear potential energies. Recall that when I talked about chemical bonding, I used the analogy of a steep-walled valley, and some arrangement of electrons are particularly stable, like boulders sitting right on the valley floor. Inert gas elements, those are like that. Well, stable isotopes are much the same. Many stable isotopes have relatively low energy. And then we saw that some arrangements of electrons are extremely unstable, like boulders that are perched high on the edge of a cliff. They're waiting to crash down. The element fluorine is a good example of a very unstable element. In exactly the same way, uranium and radium and other radioactive elements have high nuclear potential energy. They're like boulders perched on the high sides of a steep-walled valley. They're ready to fall down to lower energy states. So radioactivity spontaneously releases energy. That's energy in the form of fast-moving particles or high-frequency radiation that's quickly converted to heat. So think about where this energy must come from. If a particle with mass flies away from an atom at high velocity, then the particle is releasing energy. It has kinetic energy. Well, according to the first law of thermodynamics, energy has to be conserved. The kinetic energy clearly comes from inside that atom. So where does the energy come from? Remember the list of different kinds of energy? It was in 1905 that Albert Einstein showed that mass itself is a form of energy. In radioactivity, it's mass that gives the energy. If you measured the mass of the radioactive isotope before and after a decay event, you'll find that mass was consumed in the process. The mass of all the products of a nuclear decay is less than that of the original isotope. Some mass is always converted to energy. Now, extremely massive nuclei, it turns out, aren't the only ones that can release energy in nuclear reactions. In fact, the least massive elements also have a surprising amount of nuclear potential energy. In fact, hydrogen has absolutely the highest amount of nuclear potential energy per nuclear particle. As we'll see, two hydrogen atoms can combine to form a helium atom and lots of energy in the process. There's actually a very close analogy here to chemistry. You can combine elements in the chemical reaction of burning, and that also releases energy. So look at the periodic table and think about the potential energy stored in various nuclei. The heaviest elements, like uranium, down here are unstable. They spontaneously undergo radioactive decay. And then it turns out the lightest elements, way up at the top, they're also relatively energy rich. So what element or isotope has the least nuclear potential energy? Think about that. What's the lowest? Well, it turns out that iron 56, iron's right here in the middle of the table, and iron 56 holds that special place among the isotopes. It is the lowest nuclear potential energy of any isotope. In fact, iron 56 is the nuclear equivalent of ash. Ash is a material that has lost virtually all its chemical potential energy. You can't extract any more energy from ash. Well, the same thing's true for the nucleus of iron 56. There's absolutely nothing you can do to the nucleus. You can't add or subtract a proton or a neutron and lower the nuclear energy. For this very reason, iron 56 plays a special and dramatic role in the evolution of stars, and I'll talk about that in lecture 30. Okay, the main focus of this lecture is nuclear reactions. First, I'm going to examine nuclear fission reactions in more detail. It turns out that some heavy isotopes, most notably uranium-235 and plutonium-239, these release prodigious amounts of energy when they're split apart in the process called nuclear fission. Take a look at this. Under most situations, fission is triggered by collision with another particle, such as a neutron. Uranium-235 is an important example of this process. The isotope can be split into several fragments by collision with a neutron. Now, this process is different from radioactivity. In radioactivity, a relatively small particle, like an alpha particle or an electron, is released from a larger atom. But in a fission reaction, the products from the original nucleus are two or more large chunks of roughly equal size, plus more energetic neutrons that also are released. These nuclear chunks are themselves new isotopes that are usually radioactive. Look at the periodic table and see what happens when uranium-235 undergoes fission. It produces a number of fission products. So here's uranium, and then it commonly produces radioactive strontium-90. That's one of the alkaline earth elements over here in the second column. Strontium actually behaves chemically like calcium, and one of the greatest concerns related to radioactive fallout from nuclear tests is that calcium-rich dairy products can become contaminated with radioactive strontium, and that strontium can enter children's fast-growing bones. And then there's radioactive cesium-137 and cesium-139. It's one of the alkali metals over in the first column on the left. It can also be absorbed into the body. Then see these elements on the left side of the periodic table. Iodine-129. Iodine is concentrated in the thyroid gland. People exposed to radioactive iodine can suffer a variety of thyroid illnesses. And radioactive krypton-85, that's all the way over on the right. That's one of the inert gases, so it quickly becomes part of the atmosphere. That's similar to the behavior of radon. Fission of uranium-235 also produces energetic neutrons. Each time one isotope of uranium breaks apart, those neutrons then become available to speed out and split other uranium-235 isotopes. And if the concentration of uranium-235 is high enough, then a chain reaction is going to result. A chain reaction occurs when each fission reaction triggers new reactions in a self-sustained process. Okay, let's take a look at a great technology associated with nuclear fission reactions. That's the nuclear reactor. A nuclear reactor is a device that controls nuclear fission reactions. In other words, a reactor uses nuclear fuel to produce electricity, to produce electrical potential energy. It's basically a big machine that converts mass to some other kind of energy. In modern commercial reactors, uranium fuel, sometimes enriched in uranium-235, is shaped into long, pencil-thin rods. and these rods are encased in a zirconium metal to keep the uranium and their decay products confined. A nuclear power plant may have several hundred to a few thousand individual fuel rods, and they're arranged in easily installed units of a few rods apiece. The fuel rods are arranged in a regular pattern, so they'll irradiate each other with energetic neutrons. This process leads to a sustained nuclear reaction. There's also an array of graphite control rods, and these rods can be dropped down in between all the fuel rods. Graphite efficiently absorbs neutrons, and it can be used to shut down the reaction. And then there's a fluid. It's either normal water or sometimes heavy water that surrounds the fuel rods. That water absorbs some of the energy from the neutrons, and it gets quite hot. And that heat generated by the nuclear reactor is used to produce steam, which in turn drives an electric generator. So that's just like a coal-burning plant. You use nuclear fuel instead of burning coal to produce the heat. As of the early 21st century, there's a total of 103 nuclear power plants in the United States in 31 different states. These power plants provide about 20% of the electrical energy in the United States, and it's an ongoing debate whether or not to build more. There are real safety concerns associated with nuclear power. My wife and I own a home on the shores of the Chesapeake Bay, just 5 miles from the Calvert Cliffs nuclear power plant. And every year we get a brochure. We can see this big white power plant from our living room, and we get an annual evacuation plan, what you need to know in case of a nuclear emergency. And in the middle of this brochure it has a map which shows the power plant. We're about 5 miles northwest. And it tells you where to go and how to escape in case of a release of radioactive material into the environment. Well, that's a very unlikely event. To prevent the release of radioactive material, the central reactor core is surrounded by a reinforced steel structure. And I should emphasize that the real danger of a nuclear power plant is not a nuclear explosion. There's simply no way that can happen. But a radiation leak could be quite serious. In fact, the most serious nuclear accident in this country occurred in 1979 at 3 Mile Island near Harrisburg, Pennsylvania. A partial meltdown of nuclear fuel occurred when the reactor water escaped and the computer systems failed. That facility was effectively destroyed, but it's important to remember that there was no significant release of radioactivity thanks to the massive confinement structure that's built around the reactor core. Now, a very different situation occurred in 1986 at the Chernobyl nuclear power plant. Chernobyl is in the Ukraine near the Russian and Belarus borders. And there's a series of operator errors that occurred that led to a complete meltdown, which produced extremely high temperatures. And the confinement structure wasn't reinforced, and it basically blew up from the pressure of superheated water. And what followed was a series of massive fires, and that spewed large amounts of radioactive material all over thousands of square miles of the countryside. This was a terrible disaster. Thousands of people became sick, and many died of radiation exposure, and a huge populated land area was contaminated. No one yet knows the long-term effects on the ecosystems and the water supply of that Chernobyl disaster. Well, I can't leave this subject then without making a brief comment about risk. We have to ask ourselves, what risks are we willing to accept in exchange for a reliable supply of energy? And I think it would be naive to think that coal-burning plants are somehow safer. After all, coal mining is one of the most dangerous professions in America, and pollution from coal-burning plants contributes widely to long-term medical problems. And yet, nuclear power plants have their own serious risks, including the problem of nuclear waste disposal, which I'm going to consider later. So citizens have to decide what constitutes acceptable risks, and I don't think there's an easy answer to that question. Before we leave this question of fission reactions, I have to tell you a fascinating geological discovery. This is related to the subject. Under very unusual circumstances, it turns out that hot water can dissolve uranium atoms and then redeposit them into rich concentrations of uranium ore. Now, billions of years ago, when uranium-235 was many, many more times enriched in Earth than it is today, a few of these deposits became natural fission reactors. That is, the neutrons emitted by one uranium-235 triggered the fission of other uranium-235 isotopes. Geologists discovered these deposits in a curious way. They began to analyze the isotopic composition of uranium deposits, and they found them drastically depleted in uranium-235. See, that's the kind of uranium that's used in atomic bombs. There's 17 separate natural reactor sites that have been identified now near Oklo and Bangombe in equatorial West Africa. That's in the Republic of Gabon. The first one of these was discovered in 1972, and that's when uranium ore from Gabon was found to be depleted in uranium-235. See, at first, some people suspected that the uranium ore had been tampered with, but then further studies showed that this was just a natural process. It's now estimated that these reactions lasted maybe 100,000 years, and they produce temperatures up to about 350 degrees centigrade. Let's take a look at one of these nuclear chain reactions. If a nuclear fuel such as uranium-235 is sufficiently concentrated, then a chain reaction can proceed faster and faster in an uncontrolled explosion. The result is an atomic bomb. So here's a diagram of an atomic bomb. An atom bomb uses a few pounds of concentrated uranium-235 or plutonium-239 in a grapefruit-sized mass. That mass is split into sections that are separated, for example, by pieces of lead. This mass of nuclear fuel is surrounded by a precisely shaped charge of conventional explosives, like plastic explosives. And when the conventional explosive is set off, the sections of nuclear material are compressed together to achieve a critical mass. That sets off a chain reaction, and the uncontrolled chain reaction converts mass into intense heat, light, radiation in an instant. The first atomic bombs carried the power of thousands of tons of chemical explosives. That's a huge amount of explosive power. Still, atom bombs are inherently limited by the critical mass of the isotope that's used. If you'd like to learn more details about the amazing history of the Manhattan Project and the development of the bomb, you should read this great book by Richard Rhodes called Making of the Atomic Bomb. It's really a classic in the history of technology. Okay, so we now come to the second kind of nuclear reaction. These are called nuclear fusion reactions. In a nuclear fusion reaction, two nuclei combine to form a single larger nucleus. In other words, you start with two atoms like these two hydrogen atoms and wind up with just one atom like the deuterium here. Typically in a fusion reaction, the mass of the resultant new nucleus is a fraction of a percent less than the total mass of the original two nuclei. That means that energy is released in the process. Now, by far the most common fusion reaction in nature combines two hydrogen atoms to make one helium atom. And here's how that happens. You go to the deuterium, and then a deuterium and a hydrogen atom combines to make a helium-3, and then two helium-3s combine to make a helium-4 and two more protons. It turns out that this fusion reaction is the primary energy-producing process in the Sun, as well as in most other stars. It's just amazing. The Sun converts about 700 million tons of hydrogen into helium every second. In the process, about 4.5 million tons of mass just disappears and winds up as the prodigious heat and light output of the Sun. So roughly 0.6% of the mass of hydrogen is converted to energy. Under most circumstances, hydrogen atoms won't combine in this way. The positive charges of the two hydrogen nuclei repel each other, so the electrostatic force prevents a close approach of atoms. Instead, you form an H2 molecule in which two nuclei are separated by about a 10/1000th of a meter. The two hydrogen atoms are linked by a strong covalent bond in which two electrons are shared by the two atoms. This arrangement keeps the positive charges apart. Now, for fusion to work, the two hydrogen atoms somehow have to be forced very closely together. The only natural place where that can occur readily is inside the massive collections of atoms called stars. You see, inside stars, there are tremendous temperatures, there are tremendous pressures, and those conditions provide the energy needed to overcome the electrostatic repulsion. You can think of fusion as a process in which two atoms have to overcome a huge energy barrier. Fusion reactions are sort of like pushing a heavy boulder up a steep slope. In order to let the boulder crash down a much steeper slope, you have to expend a lot of energy in the first place, but then you get much more energy back. On Earth, scientists and engineers have been engaged in several attempts now underway to develop a nuclear fusion reactor. That's a formidable technical challenge. But such a reactor, that's one that consumes only cheap and abundant hydrogen and produces safe, environmentally benign helium, that would transform the world's energy production. Nuclear fusion reactors could provide a sustained source of relatively inexpensive energy for as far into the future as anyone can imagine. Just a few pounds of hydrogen could produce energy equivalent to many thousands of tons of coal. But for now, fusion energy is still a dream. There are lots of engineering challenges associated with designing and building a fusion reactor, and perhaps the principal difficulty is creating a confined, high-pressure, high-temperature environment. Think about that. You have to subject hydrogen to the radically extreme temperature and pressure characteristic of the Sun's interior. Quite simply, there's no known material that can hold such an extreme environment. But there are some intriguing ideas. You know, one clever strategy is to use a hydrogen plasma. That's an extremely hot gas in which the electrons have been stripped off the hydrogen nuclei. Remember, a plasma conducts electricity, so it can be heated by electrical induction. It's also possible to heat a plasma to incredibly high temperatures with powerful lasers. What's more, a plasma can be pressurized using strong magnetic fields. That's what I call the magnetic bottle. So you confine the plasma and then you heat it up. For many years, research in this kind of fusion reactor had been conducted at Princeton University at their plasma research laboratory using a device called a tokamak. The tokamak is essentially a donut-shaped vacuum chamber surrounded by powerful superconducting electromagnets. So a large current up to several million amps flows through a hydrogen plasma. As a result, the plasma is heated to temperatures more than 100 million degrees centigrade. That's much hotter than the core of the sun. And this is by high-energy particle beams or by radio frequency waves. At these extreme conditions, a tiny amount of hydrogen fusion takes place, though they haven't been able to sustain a break-even output of energy yet. Now, another strategy is to form dense pellets of a compound rich in hydrogen and simultaneously irradiate the pellet with more than 100 high-power lasers. The main center for this kind of research is the National Ignition Facility. It's at California's Lawrence Livermore Laboratories. The idea is to direct the full power of 192 high-energy lasers simultaneously onto a BB-sized hydrogen pellet. The intense light energy should cause that pellet to implode. That would push temperatures and pressures above the critical limit for fusion, and it's expected that the first major experiments of this $500 million laboratory should occur sometime in 2002. Now, so far, none of these efforts is close to a commercial plant, but the lure of abundant, cheap energy using hydrogen fuel continues to be really seductive, so keep watching the news for advances in fusion research. There's another technology, the hydrogen bomb, that was developed shortly after World War II. It also converts hydrogen atoms into helium plus energy. Scientists who worked in the atom bomb during the Second World War realized that atomic bombs, which rely on nuclear fission reactions, are inherently limited in size. You can't cram much more than one critical mass into an atom bomb. But nuclear fusion bombs are different. Hydrogen atoms are stable. So there's really no limit to the size of a hydrogen bomb. So researchers began to work on fusion weapons. And once again, Richard Rhodes has given us a wonderful book, this one called Dark Sun. It chronicles the intriguing Cold War history of developing the hydrogen bomb. The hydrogen bomb is amazing. Here's a schematic diagram of how the bomb works. The core of the bomb is a hydrogen-rich compound such as lithium hydride. Actually, rather than use normal hydrogen, the hydrogen bomb uses H3 or tritium. Recall that tritium is the hydrogen isotope that has 2 neutrons along with 1 proton. Tritium is a radioactive isotope with a half-life of about 12 years. And this is what's, to me, the really scary part. A central mass of this hydrogen-rich material is surrounded by atomic bombs. So the atom bombs are what are called triggers. When the atom bombs explode, they create enough heat and pressure to trigger nuclear fusion reactions in the hydrogen. Then that much larger explosion converts much of the hydrogen to helium with a corresponding release of huge amounts of energy. And again, because the hydrogen-rich compound is inert, the size of a hydrogen bomb is for all practical purposes unlimited. Typical modern warhead carry the equivalent of tens of millions of tons of conventional chemical explosives. The largest Russian warheads are said to be 50 megatons, 50 million tons of high explosives. That's more than enough to completely destroy any city on Earth. I should tell you about one other fusion effort that received a lot of attention. You may have read an exciting discovery a few years back called cold fusion. There were 2 scientists from Utah. They claimed that they were able to initiate a hydrogen fusion reaction in their laboratory in a simple benchtop experiment. What they did is to place 2 rods of a rare metal, platinum-like metal, called palladium in a bath of heavy water. Recall that heavy water incorporates the hydrogen-2 isotope called deuterium rather than ordinary hydrogen-1. So every hydrogen atom has a neutron as well as a proton in its nucleus. When current was applied through these palladium rods, the scientists claimed that some of the deuterium atoms fused to make helium and energy, which was measured as excess heat. Now, that's an absolutely astonishing claim. It's like getting energy for nothing out of water. They announced their result at a press conference, and eventually, after lots of prodding, they released details of the process on the internet. Well, you can imagine what happened. Thousands of researchers came to start studying this because the researchers in Utah were extremely well known and well respected in this field of electrochemistry. And this discovery promised to be one of the greatest advances in history. So all these scientists stopped what they were doing, and they attempted to duplicate the results. You see, if the process actually worked, it promised unlimited cheap energy for all the world. You could have a desktop fusion device to power all the appliances in your home. Some reporters even speculated about personal portable fusion energy supplies you carried on your belt. Well, after several weeks and the equivalent of what was really many research years of labor, the scientific community concluded that cold fusion doesn't work. Other scientists weren't able to duplicate the results, and there was no evidence that any fusion reactions were taking place. A lot of people shook their heads and pointed to the sad state of science. They said fierce competition for research funds and status was causing scientists to bypass the traditional peer review system. And some commentators even implied that the scientific method itself was at risk. But I really took a different view of this episode. Sure, a lot of scientists wasted their time, but even if cold fusion doesn't work, the scientific method does work. Within a matter of weeks, the scientific community had shown convincingly that the original experiments weren't reproducible. It didn't take a big committee. It didn't take a crisis in the scientific community, and in some ways it was a rather exhilarating time for those involved. And I take that as a kind of triumph for science. Well, before examining the benefits and dangers of nuclear technology, I want to tell you about one other application of nuclear fusion experiments. You might be surprised to learn that the periodic table isn't complete, and it may never be. Scientists continue to search for what are called artificial super heavy elements beyond the heaviest natural element, which is uranium. That's element 92. These elements are called the trans-uranium elements. Take a look at the periodic table again. The first of these super heavy elements was produced by bombarding uranium atoms with slow neutrons. These experiments were done in conjunction with nuclear reactors that produced a reliable source of neutrons. Every so often, when a neutron collides with the uranium nucleus, that neutron will just join up, and the nucleus becomes heavier by one neutron. So eventually, the uranium nucleus becomes so neutron-enriched, so packed with these excess neutrons that it undergoes beta decay, and beta decay bumps the atom up to the next higher element. So element 92 becomes element 93. That's the first of the artificial elements, neptunium. Look at this. Element 93 is right next to uranium in the periodic table. It was produced at the University of California, Berkeley in 1940. That isotope, neptunium-237, has a half-life of about 2 million years. So if you make some neptunium in a reactor, it has the decency to hang around long enough so they can be studied. For the next decade, other discoveries quickly followed. Elements 97, that's berkelium, and 98, californium. In general, the heavier elements have shorter half-lives. Californium-251 has a half-life of 890 years, for example. More progress was made by groups in Germany and in Russia and the US by attempting to fuse large nuclei together. Today, some elements have been reported up to about 118, although there's some skepticism about those. Anyway, this is amazing research. For example, isotope 277 of the as yet unnamed element 112 was created by colliding lead nuclei, that's element 82, with zinc nuclei, that's element 30, and you fuse them together and you get element 112. Only a few atoms have actually been produced, and they have a half-life of only a few hundred millionths of a second. Well, I have to end this lecture by acknowledging that nuclear technologies do bring both benefits and problems. Among the most pressing problems associated with nuclear technology is nuclear waste disposal. This waste comes primarily from used reactor fuel rods and the byproducts of nuclear weapons production. The largest site in the U.S. is at the Hanford facility in central Washington state. That's where most of the weapons-grade nuclear material was concentrated. It's a huge facility, and there are many thousands of tons of dangerous nuclear waste. See, every hydrogen bomb requires atom bomb triggers, so uranium and plutonium have to be concentrated. Usually that's done by dissolving radioactive materials in nitric acid, and what's left over are millions of gallons of nitric acid with dissolved radioactive isotopes. Waste products of nuclear fission reactions, they include all kinds of radioactive isotopes, strontium-90 and cesium-137, krypton-85. These all have half-lives of a couple of dozen years. So this lethal super is going to decay to safe levels in perhaps 300 years. But there are lots of other long-lived radioactive isotopes. The problem is with things like cesium-135 with a 2 million year half-life and technetium-99 with 210,000 year half-life. Those are going to remain dangerous for thousands of generations. The problem of confining this waste for many thousands of years is compounded by decay chains. Remember, the mix of elements under storage keeps changing because of this changing chemistry. One element decays to another, decays to another. It's difficult to find one material that holds them all. So the Department of Energy is zeroing in on a steel alloy that's supposed to be safe for 10,000 years, but really no one can be sure. No human container has ever lasted 10,000 years, especially when it's holding a highly corrosive radioactive solution. The most widely accepted solution is going to be burial of canisters in a dry, geologically inert environment. The problem is where and what sort of container. One intensely studied burial site is Yucca Mountain in a relatively remote part of Nevada. Still, this site turns out to be highly controversial. Some geologists claim that while the site is dry today, there's ample evidence for extreme changes in the level of the water table, and other geologists point to evidence for earthquakes in the not-so-distant past. And, of course, the Nevadans don't want the waste. Nobody does. And even if you find a site, many states don't want trucks to haul nuclear waste across their borders. So whatever the solution is likely to cost U.S. taxpayer many hundreds of billions of dollars, and by some estimate trillions of dollars to fix this problem. Well, in summary, nuclear reactions result from the fact that some nuclei have more energy than others. Two kinds of nuclear reactions, fission and fusion, release prodigious amounts of energy by converting some of the nuclear mass into the kinetic energy of speeding nuclear radiation. So humans have attempted to harness that energy with results that yield both significant benefits and serious problems. But by far the most important consequence of nuclear processes is the energy that Earth receives from the sun. And that's the subject of the next lecture.